Chapter 9 is on alkynes, which are all kinds of fun. Now, if you take a look at these three structures, you'll notice the first one is an alkane, the second is an alkene, and the third is an alkyne. The major difference here is the number of hydrogens attached. The first one will have complete saturation. The second one is 1 degree of unsaturation. We decrease the hydrogens by 2. The third one, we decrease the hydrogens by 2 more, and we get 2 degrees of unsaturation. The general formula for any alkane is CnH2n plus 2, where N is the number of carbons. This formula can be extrapolated to alkenes and alkynes, CnH2n and CnH2n minus 2. This example of the simplest we can get of ethane, ethene, and ethyne would have C2H6, C2H4, and C2H2 as their respective formulas. Nomenclature of alkynes will have a YNE ending. So for example, 2 carbons is ethyne, 3 is propyne, 4 would be butyne. We can specify the location of the alkyne. If I number this 1 through 4, the alkyne is at position 2, so this would be but-2-ine. Third example for nomenclature, getting a little bit more complex, will be 6-bromo, 2-methyl-hept-3-ine. Being able to name the fourth structure is going to require a little bit more knowledge of nomenclature. Hopefully you have practiced nomenclature and are ready for the nomenclature on the ACS exam. You'll notice that bromine is 6, the methyl is at position 2, and the ine is at position 3. So how would you know to number it 1, 2, 3, 4, 5, 6, rather than having bromine at position 1? Well, you need to understand the priority of functional groups. I have a list here of what has the highest versus the lowest priority, and these are in order. So bromine we looked at last. We put that on the end of the molecule as number 6 rather than 1 because it has the lowest priority. So if it was the highest priority, like an acid, we would start on the end where the bromine is and give it a number 1. So the list of priorities are acids, esters, aldehydes, ketones, alcohols, amines, alkenes, alkynes, alkanes, ethers, and alkyl halides. There's more functional groups than this, but this list gets you through the majority of structures that you'll see for nomenclature. So let's go back and look at alkynes, and want to just start very briefly and discuss the physical properties of alkynes. These are hydrocarbons, so they're nonpolar, and because they're nonpolar, they'll be insoluble in water. Electronic structure. These alkynes are made up of 1 sigma bond and 2 pi bonds. I have a little structure here shown with color coding. The sigma bonds are labeled in red, and we're going to have 2 pi bonds. And again, a pi bond is made up of 2 half interactions. So for example, this blue top and bottom represent 1 pi bond, and then in neon green we have a second pi bond. So the blue and the green would represent the 2 extra bonds other than the sigma bond. Now, because of the very close interaction of the 2 carbons within this triple bond, there's going to be some unique reactivity that we can get. If you have a hydrogen that's directly attached to an alkyne, it's actually acidic in nature. It's very easy to pull off because the lone pair of electrons that would be left on the carbon is stabilized by the neighboring alkyne. Let's take a look at this. These are called acetylide ions. We need to have a terminal alkyne, so we need a triple bond at the end of a molecule where there's a hydrogen. We need a strong base to be able to pull off this acidic proton. Something like hydroxide and alkoxide, those aren't going to be strong enough. So those are what we think of as usual strong bases, and since they aren't going to work so well, what should we use? Well, what's commonly used is called sodium amide, and it's going to be made up of the NH2. So notice nitrogen with 2 hydrogens and 4 total lone pair of electrons. The 4 lone pairs of electrons will give nitrogen a formal charge of -1. This is what can be used to pick up the acidic hydrogen, which I've highlighted here in red. So you'll notice it needs to react with a terminal alkyne. So we need an alkyne that is on the end of a molecule so that you have a hydrogen on the end. Whereas if you have an internal alkyne, it will not have a hydrogen on the end, like this example that has 2 methyl groups. There's not an acidic proton. So if we react this with sodium amide, there will be no reaction. So with the terminal alkyne and the acidic hydrogen, we can react this with sodium amide. We're going to produce our acetylide ion, as shown here, as well as sodium and ammonia. So this will still be overall neutral because when this nitrogen uses its lone pair to pick up a hydrogen, it will be left with neutral ammonia. So there's a few different types of reactions that you can perform once you have your acetylide ion. Acetylide ions can be very strong nucleophiles. For example, in substitution reaction, you'll remember from chapter 6, there are SN2 reactions which require a very strong nucleophile. So here's an example with methyl iodide. You can see I have the red arrow coming in. This is acting as a strong nucleophile, coming to this partially positive carbon, sending off the iodide leaving group. This will form a new covalent bond and you'll get a methyl attached. So I have circled here in blue whatever our alkyne piece is, and whatever the alkyl halide is the alkyl group will be in green. So you can get an idea of how you can start to piece together molecules and be able to attach some type of alkyne to another alkane group. This will produce sodium iodide as a side product. Acetylide ions are also strong bases. So this would be like an E2 reaction. So let's write E2. So in this elimination reaction, you can see this alkyl halide is too bulky. It's going to have these 2 methyl groups that are going to block the acetylide ion from coming in to attack this as an SN2 reaction. Instead, it's going to grab one of these outside hydrogens. So I have it shown here grabbing this hydrogen. We're going to grab the hydrogen, leave the electrons, which will swing over, form an alkene bond, and then send off the bromine. We'll produce sodium bromide salt. The acetylide will pick up a hydrogen, and then our main product here will be an alkene. Another type of reaction that you can see with the acetylide ion is addition to carbonyls. Here I've just labeled it as a nucleophile with NuC and a minus charge. So you'll remember that a carbonyl has a C double bond oxygen. The oxygen's partially negative, the carbon's partially positive, so the nucleophile will be attracted to this because of the dipole. So once this attaches in a covalent bond, it'll break the carbon-oxygen double bond and form this alkoxide ion, which in the presence of water will form an alcohol. I want to go through 3 example reactions with the type of carbonyl. The first will be formaldehyde, which is the simplest aldehyde shown here where we have 2 hydrogens. So it's the only type of aldehyde that has double hydrogens. It's kind of like a double aldehyde. When it reacts with the acetylide ion, which I've shown here where we have our carbon-carbon triple bond and our negative charge, we're going to produce a primary alcohol. Now, any other type of aldehyde that's not formaldehyde, so we'll have an alkyl group and a hydrogen, this will produce a secondary alcohol. And then if we don't have any hydrogens, so just alkyl groups, this will give us a regular ketone, will produce a tertiary alcohol. So let's take a look at the mechanism of formaldehyde with the acetylide ion. You're going to have a nucleophilic attack on the carbonyl. We'll send the electrons up onto the oxygen to form our alkoxide as shown here. So now we have our new covalent bond. in the presence of water, or acid actually, this can pick up a proton and we're going to form our primary alcohol. Here's an example all the way from an alkyne. So first we need to form our acetylide ion using that really strong base, the sodium amide. Here's our structure of formaldehyde, or the chemical formula, I should say, H2CO. And then in the presence of acid, we'll get that hydrogen, as we just showed here, the alkoxide to the alcohol. This will give us a primary alcohol. The next type of reaction is using the acetylide ion with an aldehyde. Only difference here, instead of two hydrogens like in formaldehyde, we're going to have one alkyl group. We'll have a nucleophilic attack, send the electrons up onto the oxygen, form our alkoxide, and then in a little bit of acid, we'll get our alcohol. This time it'll be a secondary alcohol because we have two R groups. Here's an alkyl group, and then this alkyne that's attached will act as our other alkyl group, so secondary. The last type of reaction will be with the ketones, so this will have two alkyl groups attached. Same mechanistic pathway in that we have a nucleophilic attack on the carbonyl, send the electrons up onto the oxygen to form our alkoxide. In the presence of acid, this will transform that to the alcohol. And as you can see, because we have 1, 2, 3 R groups, this will be a tertiary alcohol. So while it's fresh in your mind, I just want to review. You can see the reaction with formaldehyde will give us a primary alcohol. Reaction with any other aldehyde that has at least one alkyl group will give us a secondary alcohol. And then with just a regular ketone where we have two alkyl groups, we'll get a tertiary alcohol. So let's take a look at how we can form alkynes. We can do this from elimination reactions. Here's two examples. Using two different types of dihalides. In the presence of base, you can see we can have the halogens leave to form the alkene, and then continue adding enough base to form the alkyne. So here's two examples of that. Now, from the alkene, we can actually have a little bit of control to get either an internal alkyne or a terminal alkyne, depending on the type of base we use. So for example, here in red, if you use potassium hydroxide and 200 degrees Celsius, you'll get an internal alkyne. Whereas if you use a stronger sodium amide, 150 degrees Celsius, and acid, you'll get our terminal alkyne, where we actually have the carbon triple bond carbon with the hydrogen that could form the acetylide ion. Here are two example reactions illustrating the use of potassium hydroxide at the top. Here's a dibromo alkyl halide, so you can see that we'll form an internal alkyne. So notice here we have a methyl group on the right and an ethyl group on the left. So no hydrogen. So if we reacted this with sodium amide, nothing would happen. On the bottom, here's a dichloro example using sodium amide, 150 degrees Celsius, and acid. We're going to get a terminal alkyne, and this is unique because it's at the end of a molecule and will have a hydrogen. It'll have that acidic hydrogen that we can do chemistry with. So this is the end of part 1 of alkyne chemistry and alkyne reactions. Please check out part 2 to look at more alkyne reactions. Thank you.